For centuries, people looked up at the night sky and saw a fixed, immovable stage. The stars seemed firmly anchored in place, while Earth moved beneath them. Under Isaac Newton's laws, gravity pulls on mass. Since light has no mass, gravity shouldn't be able to pull it. A beam of light should travel through the universe in perfectly straight lines. But in 1919, astronomers pointed their cameras at stars near the sun and observed something impossible. The stars weren't where they were supposed to be. They had moved. That single observation proved the rules governing the universe for hundreds of years were incorrect. The story begins with a paradox that troubled Albert Einstein. Newton's gravity was believed to act instantly across space. If the sun suddenly vanished, Earth would supposedly feel it immediately. But Einstein knew absolutely nothing, not even information, can travel faster than the speed of light. He spent years wrestling with this. To solve it, he imagined a person trapped inside a sealed elevator. If that elevator accelerated upward, objects inside would fall to the floor. But place that same elevator on Earth, and gravity does the exact same thing. Inside the box, you cannot distinguish the two situations. That realization became the seed of a new idea. Gravity isn't an invisible tether pulling objects together. Imagine a heavy bowling ball sitting on a stretched rubber sheet. The fabric warps downward under the weight. Roll a marble across that surface, and it curves toward the ball. Nothing is pulling it. The marble is simply following the shape of the surface beneath it. Einstein suspected that space and time themselves behave similarly. Massive objects distort the physical geometry of reality. Planets, moons, and even light follow those curves. Space is a dynamic, bending fabric that dictates the movement of everything in the cosmos. Translating that geometry into mathematics was brutally difficult. It took years of dense calculations, altered predictions, and corrected mistakes before Einstein finally completed the theory of general relativity in 1915. His complex equations made a startling prediction. A ray of starlight passing close to the sun should bend by exactly 1.75 arcseconds. An arcsecond is a microscopic measurement, just 1/3600th of a degree. Detecting a shift this small is equivalent to watching a coin move a few centimeters from several kilometers away. And there was a massive physical obstacle to testing this. The sun is overwhelmingly bright. It entirely obscures any distant stars sitting behind it in the daytime sky. The only way to verify this math was to wait for nature to block the sun. A total solar eclipse would offer a few precious minutes of darkness, a fleeting window to photograph the stars and map the true shape of reality. Astronomer Arthur Eddington immediately recognized the stakes. For the May 1919 eclipse, his teams transported sensitive optical equipment across oceans to the island of Príncipe and to Sobral, Brazil, constantly threatened by clouds and weather. As totality approached, temperatures dropped and daylight faded. The moon perfectly blocked the sun, and the surrounding stars finally emerged against the black disk. The cameras began recording. Teams frantically captured exposure after exposure on glass plates, knowing they had only minutes before the sunlight returned and ruined the test. Back in England, the reality of scientific fieldwork set in. Heat had warped the equipment in Brazil. Some images were blurred. The measurements across the photographic plates were messy and varied wildly. It suddenly appeared that years of calculation and a massive global expedition might produce no answer at all, with Einstein's physics threatening to collapse purely due to unreliable terrestrial weather and flawed optics. Eddington persisted. He isolated the clearest plates and repeatedly measured tiny fractions of millimeters to eliminate errors. This chart plots the expected results. Newton's classical rules predicted a slight bend of roughly 0.87 arcseconds. Einstein predicted 1.75. The most reliable measurements from the clearest plates clustered closely between 1.6 and 2.0 arcseconds. Einstein was right. To understand how light bends without being pulled by a force, imagine drawing the shortest route between two cities on a flat map. The line looks curved, but when that map wraps onto a globe, you realize the path is actually perfectly straight.
General relativity shows that light does exactly the same thing. The physical stars behind the sun never moved. Space itself was warped, and the light simply traveled the straightest route available through that curved geometry. Today, our technology relies on this geometry. Modern satellites constantly correct for the relativistic effects of Earth's mass. If we ignored Einstein's equations, GPS errors would accumulate by kilometers every single day. Astronomers observe this daily through gravitational lensing. Massive galaxies act as cosmic magnifying glasses, bending light from objects behind them into stretched, glowing arcs. Scientists use these visual distortions to map invisible dark matter and study objects far too distant to see directly. Starlight crossing the cosmos arrives at our eyes only after traversing millions of years of warped, bending geometry. Our familiar, straight-lined universe is an illusion. And if something as obvious as the night sky is secretly curved, it forces us to ask what other features of reality look perfectly obvious until someone finally measures them.